Good evening, everyone. My name is Vinay. I'm a volunteer for North South, the workshops team. And today we're having a AIME live problem solving session. I'll introduce to you Sri Priya. Sri Priya Raman is Dr. Sri Priya Raman is our coordinator for all our AP classes, and she has an excellent team that has also supported AMC 8, AMC 10, AME prep classes, and also we are starting the Physics Olympiad and Biology Olympiad classes as well. So we have with us a few of the volunteers from her team who will be presenting the AIME live problem solving seminar today. Over to you, Sri Priya. Sri Priya, I think you're on mute.
Thank you, Vinay. Good evening, everyone. Thank you very much for joining with us on a Saturday evening. It's a pleasure to host this live solving session for AIME. We have 3 panelists who are extremely knowledgeable, and we are lucky to have them here with us on our team to conduct the AIME workshops that we just completed a few weeks ago. And this is a live solving session. And we plan to have AMC 10, 12, and AIME workshops again in summer. So please be on the lookout. Hopefully we'll recruit enough coaches to have sessions again on summer. We've been doing this for the last 2.5 years. Today we have Rushabh Mehta, who is super passionate about problem solving. He's an adult volunteer for our team. He has written questions for competitions like MMaths. And Rushabh is a graduate of University of Chicago, where he studied algebraic geometry. He currently runs an AA firm in New York. Thank you, Rushabh, for joining us. We also have Ram Sivaraman, who is a high school student. He is passionate about science, math, and music. Ram has competed and won several competitions like Science Bow, Science Olympiad, Math Counts, AIME, and several other competitions. He also loves to play violin. He hopes to study computer science and engineering and signal processing in college. And Ram has been our volunteer for ever since we started our team about 3 years ago, or maybe even longer now. So we are very happy to have him with us. We also have Savitri Sivaraman, who is our parent volunteer for our team, and she helps us coordinate and leads multiple subject classes for us, including AP Physics, AMC 10, AMC 12, and AIME. I don't know how she does it, but she keeps us strong to do our classes in that. So thank you, Savitri. And without further ado, please go ahead and start. Thank you.
So 1 second. So this session is being recorded, so we will try to make it available in our North South YouTube channel as well. So we suggest all the attendees to also subscribe to our YouTube channel. So we'll try to post this within the next week. Before we start, we have a couple of questions to just know who are among the attendees. So if you can just select some which grade you are in, and then we'll try to have a better idea as to who's in the audience. You see a lot of you are in 8th and 9th grades. Okay, so let me just close the poll. Share results. 1 second. So we have 60% in 8th grade or less, and 32% 9th grade, 7% 10th grade. Okay, and 1 second. We also have So if you can mark as to what which of these exams have you taken. Since it's an AIME session, we assume probably you already have taken AMC 10 or 12. Most of you probably looks like 8th and 9th, so AMC 10. Okay, 78%. Okay, so let me just share results. So, okay, so 29% have taken AMC 10. And more. Well, I guess this we can leave.
So Vinay, was it 29% took
AMC
AMC 10 and the rest have not taken any of those tests?
Yeah, it appeared so. That's what probably they've taken AMC 8 and now
Yeah,
trying out.
so maybe Savitri, before we start, maybe you can give a quick review on what these competitions are so we're familiar.
Okay, so 1% okay, 1 second. I have done USJMO. I see. Okay, so it's good to know. I think there's one last. Will you be interested? Okay, so yeah, like Sripriya mentioned, there might be an AIME prep workshop or AMC 10 and AMC 8 as well. So let us know if you're interested, and then based on that, that may help the team plan for it. Okay, so I think a lot of people said they're interested. So okay, so that helps. So over to you, Rishabh, Savitri and Rishabh.
Okay. Rishabh, you want to go ahead and explain what is AMC and then AIME, or
Sure.
you want me to go through?
I can take it. So,
Okay.
hello everyone. I'm Rishabh, one of the instructors in the AIME session that we just conducted. So happy to see the turnout here. The AMC series of competitions is a series of competitions that was launched, I think, around 50 or so years ago in order to really find the best mathematical students in the country. So in the way that the international mathematics competitions work, every country wants to find their 6 best kids and send them to an international competition for them to represent their country. And the way that the US selects their kids is starting with a set of competitions called the AMCs. So some of you might have taken the AMC 8, which is a test meant for students who are in 8th grade or below. Some of you might have taken the AMC 10, and some of you might have taken the AMC 12. All these competitions are relatively shorter competitions, so roughly 75 minutes. And you solve a series of multiple choice questions, and depending on your score on the AMC 10s and 12s, you can potentially qualify for the next level exam, which is known as the American Invitational Mathematics Exam, or the AIME. So the AIME is a little bit different than the AMC competitions in the sense that it is around 3.5 hours, if I'm not mistaken. And instead of 25 questions, there'll be only 15 questions. So as you can imagine, these problems are somewhat more intensive, but you also have more time to answer them. But crucially, the test is not a multiple choice test. Instead, answers range between 0 and 999. So guessing is no longer really an option. And if you happen to have a good combination of scores on your AMC score and your AIME score together, you can qualify for the USA JMO if you took the AIMC 10, or the USAMO if you took the AIMC 12, which are competitions where you'll get an even longer period of time for a shorter number of questions. But these questions are proof questions. So no longer will they be questions that ask you to produce a number, but rather they'll be questions that ask you to prove or derive some truth about mathematics. So all these competitions are trying to find a certain set of kids to represent the United States, but are equally enriching just by themselves. Savitri, would you like to add anything else to that?
No, I think you covered everything. Thank you. Thank you. Yeah.
All right. So in today's section, we're going to go over problems from the first AIME that was issued this year. So if we have time, we'll go to the second AIME, but we're just going to go incrementally through the problems, solve them, and we'll see where it goes. So let's get started. All right. So problem number 1, let's read together. Every morning, Aya does a 9-kilometer walk, then finishes at the coffee shop. One day, she walks at S kilometers per hour, and the walk takes 4 hours, including T minutes at the coffee shop. Another morning, she walks at S plus 2 kilometers per hour, and the walk takes 2 hours and 24 minutes, including T minutes at the coffee shop. This morning, if she walks at S plus 1/2 kilometers per hour, how many minutes will the walk take, including the T minutes at the coffee shop? So our first observations when we read this problem are that each sentence relatively or essentially conveys one equation worth of information. So let's look at the first sentence. So Aya is taking a 9-kilometer walk and she finishes at the coffee shop. Then she walks at S kilometers per hour, and this walk takes 4 hours, including T minutes at the coffee shop. So what that tells us is that we have T, which is how long she takes at the coffee shop, plus the amount of time she takes to do the walk, which by the equation, which I'll write up here, distance equals rate times time, is going to be, and we can rearrange this to get time isolated, distance divided by rate is equal to time. We have the distance, which is 9, divided by S, is equal to 4 hours, which will convert to minutes, which is 240 minutes. Now, the second sentence tells us that if she walks at S plus 2 kilometers per hour, including T minutes at the coffee shop, so that is T plus 9 over S plus 2, she takes 2 hours and 24 minutes, which is 144 minutes. So given these two facts, we can solve for T by isolating T on both sides. So what do we know? If we subtract these equations from each other, we have 9 over S minus 9 over S plus 2 is equal to 240 minus 144, which is 96 minutes. Second, which is great. Now we can multiply both sides by S times S plus 2 in order to remove the denominators. So we get 9S plus 18 minus 9S is equal to 96 times S times S plus 2. Now this cancels. So we have 18 is equal to 96 times S plus 2, which becomes 96s squared plus 192s. All right. Sorry, 1 second. Vinay, are you on the line?
Yes, I'm here.
I don't seem to see the eraser function. It's disappeared from my screen.
Do you want to remove the maximize and see?
Sure, I can remove the maximize.
This is from the Google Classroom itself. I mean, sorry, the Google Sheets itself, or
this is from the GoToWebinar.
no. So the pen you're using it on the tablet, right? So
Yes. So the pen is from the GoToWebinar, but yes, it's from the tablet.
Not sure about. I think as presenter, I think I don't see those options myself.
Okay. Let's see. I think I found it. Okay. All right. Sorry about that. All right. That's fine. So I can continue without that for now. Let me reset the slideshow. All right, we can continue. So when we solve this out, we can see that this can be factored, and that factoring becomes, actually before we factor, we can divide everything by, so the common factors here between 96 and 18 is, we can divide both sides by 6. So that gives us 3 is equal to the 96 divided by 6. 16 squared plus 32s. Now we can factor here, which gives us 4s 4s minus 32. Sorry, my pen is just not working right now. All right, that's fine. I can just continue with this. So that's fine. I don't have room here, but apologies about the technical difficulties. But if you solve this out, you'll find that S is equal to 2.5 kilometers per hour, and with that, you are able to find that if she walks at S plus 1/2 kilometers per hour, so S plus 1/2, which is equal to 3 kilometers per hour, then she will reach her destination in 180 minutes. And then she spends 24 minutes at the coffee shop, which you can find by plugging this back in. And that will give you 204 minutes. All right, so sorry for the technical difficulties on that. Hopefully we should be good to go on the next problem. But I'll write that up. Like a pointer. All right, so the second problem. This problem.
A quick
Yes.
question on the previous one.
Sure. Let me go back.
Yeah. So you never changed the speed from kilometer per hour to kilometer per minutes, right? But the time is in minutes. Is that okay? Did it cancel out somewhere? Maybe.
Yes. So because of the technical difficulties, I was not able to or you were not able to see the writing on the bottom, but essentially we have two systems of equations which you can solve to find the you have two systems of equations and two variables, right? So we have two variables and s and t, and then two linear equations. So with those two, you can find both s and t. And from there, we can plug in s and t into the final sentence, which is of the following form. So we have with distance equals rate times time, we know that 9 over s plus 1/2 plus t is our desired quantity. So plugging in those values that we mentioned before will give you the answer of 204, which we can solve, but for some reason my writing under the screen is not showing. But let's move on to the second problem. I think this is, we are a little bit shorter time, so I want to make sure that we get to the problems that are a little bit more intensive. All right. So problem 2, we have two real numbers, x and y, with x and y both greater than 1 that satisfy this relatively complicated equation. What is x times y? Now, this problem obviously requires an understanding of logs, but it's not immediately obvious how to tackle this. But we have a few hints here that allow us to get started. So the first thing that we can observe is that whenever we have the following setup, we have log base a of b to the c. This is equal to c times log base a of b. And we can observe this really simply because if we raise both sides to the a to the both of these sides, we get a to the log base a of b to the c is equal to a to the c log a of b. Now, by exponentiation rules, the right side can be written as a to the, in parentheses, log a of b to the c. And this, by log rules, is going to be equal to b to the c, which by log rules, this is equal to b to c. So with this rule, what do we know? We know that x times log base x of y is equal to 4y times log base y of x is equal to 10. Now, how do we continue here? Well, there's a sneaky observation that we can make here between these two quantities. If I have a value a, such that a or in such that x to the a is equal to y, then if I raise both sides to the 1 over a, that will give us the following equation. So this tells us that a, which is log base x of y, and 1 over a, which is log base y of x, are reciprocals. So this suggests to us that we should multiply these two equations together. So what do we get? We get 4xy times log base x of y times log base y of x is equal to 100. But these two are reciprocals, so they cancel out. So that tells us xy is equal to 25. Cool. Let's head to the next question. All right. Alice and Bob play the following game. A stack of n tokens lies before them. The players take turns, with Alice going first. On each turn, the player removes 1 token or 4 tokens from the stack. The player who removes the last token will win. Find the number of positive integers n less than or equal to 2024, such that there's a strategy that guarantees that Bob wins, regardless of Alice's moves. So how do we approach this problem? Well, if you don't have any clear approach, the best way to get started on these kind of problems is to try some example values and see if you can find a pattern. So let's start with 1. If there's 1 token in our stack, then Alice wins. Why? Because Alice will simply take the 1 token on the stack and remove it. Simple. And that makes her the last player, or that makes her the player that removed the last token. What about 2 tokens? I claim that Bob wins. Why? Well, Alice has no option to remove 4 tokens. So she'll remove 1 token. And after she removes 1 token, Bob can remove the last token and win. What about 3 tokens? I claim that Alice wins. And that's because she can remove 1 token. Then Bob has to remove 1 token because there are only 2 tokens left in the stack. And then Alice will win again. What about 4 tokens? Alice wins again. And that's because she can just remove all 4 tokens. Now, what about 5 tokens? Well, the answer is Bob wins. And that's because when I'll say A takes 1, Bob takes 4, and vice versa. Now, there's something important to consider in this final case, the case number 5, and that is that this strategy creates what we call an invariant. An invariant is a quantity that stays the same no matter what strategy or what approach the players take. And invariants are a super useful way to get a grasp over complicated games. Now, why is this an invariant? The reason why it's an invariant is because no matter what Alice does, if there are 5 or more tokens on the stack, Bob is able to guarantee that after Alice and Bob both conduct their turns, the stack has n minus 5 tokens. Now, why is this important? Well, what this means is that let's say that there are n tokens, then Bob can guarantee that now there are n minus 5 tokens after both of them have a turn, then n minus 10, then dot dot dot, all the way up to n mod 5, where n mod 5 is the remainder as n is divided by 5. So what does that tell us? That tells us that if the number of tokens is of the form 5k, where k is some integer, or 5k plus 2, then Bob wins. If it's anything else, then Alice can leverage this invariant that we just mentioned to get to a winning state for her. So otherwise, Alice wins. So what this problem is essentially asking us is how many numbers are of these two forms that are less than or equal to 2024? Now, how do we figure that out? Well, how many multiples of 5 are there less than 2024? That's simply 2020 divided by 5, which is 404. How many numbers of this form, 5k plus 2, are there below 2024? Well, it's the same as the number of multiples of 5, but there's one more, 2022. So there are 400. So there are 404 of these, 404, and there are 405 of these. So our answer is the sum of those two, which is 809. Cool. Let's continue.
There are a couple of questions, so I'm going to read it out to you. First is, I do not understand what invariant is, by Harsha.
That's a great question, Harsha. So an invariant is a quantity that does not change. And when we are looking at problems where either there are multiple players in a game or there are a situation with a lot of moving parts, we often look for invariants because invariants are quantities that we can know will not change no matter what players choose to do or regardless of what happens in the game. So in this problem, the invariant of choice is the fact that either Alice or Bob can guarantee that after both of them move, the total stack, the number of tokens on the stack drop by 5. Why is that the case? Well, whenever Alice takes 1 token, then Bob can take 4 tokens. And whenever Alice takes 4 tokens, then Bob can take 1 token. And this forms an invariant that essentially guarantees that Bob can systematically drop the number of tokens in the pile from n to n minus 5 to n minus 10, all the way down to the remainder of n as it's divided by 5. Now that's great, but Alice can also leverage the same strategy by taking a first move of her choice and then playing the same game, taking the opposite number of tokens that Bob did to make sure the stack drops by 5. That's what makes this game, or 5 tokens, the invariant of this game. Does that make sense?
So sorry, maybe this is, answering, there are some 3 questions which are very similar. So why did you stop at 5 tokens specifically? And why 5k plus 2? How are you able to determine who wins each number when you don't know n?
That's a great question. So all these questions, essentially you're asking, I only did 5 cases. How do I know that for all 2024 of the games that we're presented with, I know who wins and who doesn't win? And the answer is really, really simple, which is I'm analyzing games by understanding what games occur once a certain number of moves happen. So let me say this a little bit differently. Let's say that there are 10 tokens, 10 tokens on the stack. Okay. So if Alice chooses to take one off, then we have 9. Then I claim that Bob will want to take 4 off. So after Bob's move, there are 5 tokens left on the stack. And now I know by this rule that Bob wins because we just figured it out. Now, what if there were 15 tokens? So I'm going to draw a new box. What if there are 15? Then Alice can take 1 or 4. So Alice takes 1 or 4. And then Bob can take 4 or 1, depending on what Alice took. But whatever he does, the stack will have 10 tokens afterwards, which we know by the logic over here leads to Bob's victory. So essentially what we're saying here is that Bob can guarantee that after Alice and Bob both made a move, that the total number of tokens on the stack has reduced by 5. And once we have that guarantee, then we know that there are 2 winning states for Bob that are, in the 5 that we looked at, where there are 2 tokens left in the stack and there are 5 tokens. So we know that if the number of tokens start with 5k, where k is some integer, or 5k plus 2, then Bob can systematically drop that down until he reaches a state where there are 5 tokens left in the stack, or there are 2 tokens left in the stack. In other words, right, we understood bigger games by understanding the smaller games. All right, I'm gonna take the silence to mean everyone understands the solution here, or at least to the best of their abilities. So let's move on. All right. All right, so next problem. Jen enters the lottery by picking 4 distinct numbers from S, which is a set of 1, 2, 3, all the way to 10. 4 numbers are randomly chosen from S. She wins a prize if at least 2 of her numbers were 2 of the randomly chosen numbers, and wins the grand prize if all 4 of her numbers were the randomly chosen numbers. The probability of her winning the grand prize, given that she won a prize, is m over n, where m and n are relatively prime positive integers. Find m plus n. So the first observation you might have here is the last bit of this question, which is this part, seems a little bit weird, but this is what I like to call the AIME clause. And what I mean by this is AIME often writes these kind of sentences in order to convert a non-integer answer into an integer answer so that they can ask questions with all sorts of different answers, right? Because as I said before, AIME's answers have to range between 0 and 999. So this tells us that our question has an answer which is a fraction. Great. So how do we approach this problem? Well, what do we know? We know that Jen has picked 4 distinct numbers, and there's no real information other than that about which numbers Jen picked. And because it shouldn't matter what numbers Jen picked, we can use the statement WLOG, which stands for without loss to generality, to assume Jen picked 1, 2, 3, and 4. Great. So we're told that she wins a prize if at least 2 of the numbers were the 2 of the randomly chosen numbers. And she wins the grand prize if all 4 numbers were the randomly chosen numbers. So let's think about this. How many ways are there? The number of ways for her to win the grand prize. Think about it for a moment. The answer is 1. And that's because we're picking 4 numbers, and the only way that she wins the grand prize if all those 4 numbers are 1, 2, 3, and 4. So there's only one way for that to happen. And what we're asked is we want to find the probability of her winning the grand prize given that she won a prize. So what we're looking for is number of ways for her to win a grand prize divided by number of ways for her to win a prize. Right? But we already know that the numerator is equal to 1. So all we need to do is find the denominator. So let's do that on the next slide. All right. So we were looking for the number of ways for her to win a prize. So there are 3 cases here. So case number 1 is that 4 of her numbers were chosen, aka she won the grand prize. And we already saw that there's only one way for that to happen. Now, what about the case where 3 of her numbers were chosen? Well, that means that if I outline the numbers 1, 2, 3, 4, and then 5, 6, 7, 8, 9, and then 10. The 3 numbers come from here, and 1 number comes from here. So this can be done in 4 choose 3 ways, and this can be done in 6 choose 1 ways. So the number of ways this can happen is equal to 24. And the final case is where 2 of her numbers were chosen. All right, so you can see that from here, we have chosen now, instead of 3, we're choosing 2 numbers. So if I do it again, 1, 2, 3, 4. So from here, we're picking 2 numbers. And from 5, 6, 7, 8, 9, 10, we're picking 2 from here. So that's 4 choose 2. And that's 6 choose 2. And their product is equal to 90. Great. So with all of that together, we know that the total number of ways that she can win a prize is equal to 90 plus 24 plus 1, which is equal to 115. So the final fraction is 1 over 115. And given the AIME clause, our answer is 1 plus 115, which is equal to 116. Does anyone have any questions about that?
There's some generic questions on basically what is 4 choose 3 and 6 choose 2. Maybe
Great
one
questions.
example on, yeah.
Yeah, so I'm gonna create a little box here to answer that. Actually, I can just erase this. I'll keep it here. So that's a really good question. So when I say 4 choose 3, right, that represents how many ways from a set of 4 objects, so 1, 2, 3, 4, can I pick 3? So let me try to write them out, right? So one possibility is 2, 3, 4. Okay, that's one possibility. I'm going to box it. Another possibility is 1, 3, 4. Another possibility is 1, 2, 4. And the final possibility is 1, 2, 3. So that tells us there are 4 different ways that I can pick 3 objects from this group of 4. So when I say 6 choose 1, that's essentially saying how many ways are there to pick 1 object from 6? Which you might guess is 6, and you'd be right. So choose or is a fancy way of just saying I want to pick out X number of objects from a set of Y objects in a way that I don't really care about what order they appear in. And there's some nice formulas that can help you compute, choose. So if you know what the factorial function is, then we have the following formula. So m choose n is equal to m factorial divided by n factorial times m minus n factorial. And you can think about why this makes sense. The reason why you might think so is you take, in this case, let's say 4 choose 3. I have the numbers 1, 2, 3, 4. If I want to select, let's say, 3 of them, then realistically, all I care about is I want to pick one number, then a second number, then a third number. So that's going to be 4 options times 3 options times 2 options. But I don't care what order they appear in. And there are 3 factorial ways of arranging them. So I divide by 3 factorial. And that gives me 4. So you can think about how to derive this formula. Does that make sense?
One more common question is how do we know the order does not matter or does matter?
Really good question. So let's read the question one more time. So actually, mind that. Okay. I'm going to clear out my drawings. Okay, so if we read the question, it says 4 numbers are randomly chosen from F. AIME is very, very careful about the words they use. If they tell you that 4 numbers are chosen from S, that tells you that it's as if you're taking a grab bag of numbers and I'm picking 4 out, right? They're not telling you they're picking one number, then they're picking another number, then they're picking another number, then they're picking another number, right? If they told you that, then that'd be implying that the order in which they pick the numbers is important. But here, they're just telling you they're picking 4 numbers. In whatever order, they're just choosing them from S. So you can tell that they don't care about order based on the words they use. All right, great. Let's move on to the next problem. Okay, this one. rectangles ABCD and EFGH are drawn such that DECF are collinear, which you can see in the diagram. Also, A, D, H, and G all lie on a circle. If BC is equal to 16, AB is equal to 107, FG is equal to 17, and EF is equal to 184, what is the length of CE? So let's label the diagram with the numbers they've just told us. All right. So they've told us that BC is equal to 16. AB is equal to 107. FG is equal to 17. And EF is equal to 184. I'm just going to highlight that. And they're looking for the length of CE. Now, what else do we know? We know that A, D, H, and G are concyclic. So they all lie on a circle. This should ring a few bells in your head for different circle results you can use. So what are circle results that are relevant here? Well, one of them is the fact that we have a quadrilateral which is inscribed in a circle. So we call this a cyclic quadrilateral. And there are many, 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 many nice properties of these quadrilaterals. And you can solve this problem by leveraging the nice properties of these quadrilaterals. But today we're going to use a different result. And that result is called the power of the point. So what does the power of the point say? It says the following. If I have a circle like this, right? And if I have 4 points on that circle, and now if I draw them out, okay, I'm going to call this A, B, C, and D. Then, and let's call this O, then we know that AO times OC is equal to BO times OD. It's as simple as that. But this is a super, super, super useful circle fact that shows up all the time on both the AMC and the AIME. So where can this be relevant for us? Well, we have 4 points on a circle, so we can use it to find the power of the point. So I'm going to draw, we have AD and HG as two different chords of our circle. So I'm going to extend them both like this until they meet at a point which we'll call P. So what do we know? We know that PA plus times PD is equal to PH times GH. You might think, how is this helpful, right? How does this help in any way in solving this problem? And the reason why this is helpful is because we know almost every single quantity that's listed out in here. So if we look back at our diagram here, what do we know here? We know if we label the value, if we look at PA is equal to 16 times 17, or plus 17, which is equal to 33. Okay, PD is equal to 17 because of GF. And now we have pH, which is equal to ED. And we have PG, which is equal to ED times 184. So now we have a quadratic formula with the variable being ED, which I'm going to call X. So if I isolate X to one side, we have X squared plus 184X minus 33 times 17 is equal to 0. Now you might look at this and say, great, but how do I factor this? Well, there's no easy way to factor this, but we can use something which is called the rational root theorem. And this is super useful here because in a lot of AIME problems, whenever you end up with any kind of polynomial, you can usually assume that there are generally going to be some nice roots to that polynomial if that's the intended solution to the problem. So why not take a shot in finding those? Sorry, yes?
So I think the right hand side, should it be pH dot pH times PG?
Yes, sorry. That's right.
Plus 184, right?
Yes. Very good. Let me just fix that. So pH times PG. That's right. Yeah, and the reason why is because if you look at this formula, right, here BO and OD, right, that's pH and PG, right? Both in the power of the point, P has to be involved in every single quantity. So yeah, that's good catch. Thank you.
Thank you. And also ED plus 184, right?
Yes, plus 184. Yeah, thank you for those corrections. So with the rational root theorem, what we know is that if we have a polynomial that's monic, which means that the exponent or the coefficient of the square term is 1, then rational roots will have a numerator. So if a root is equal to P over Q in reduced forms, then P will be a divisor of the last value here. So 33 times 17. Okay, so let's try out different values of P. The smallest one is, of course, 3. So if we plug in 3, we get 9 plus 184 times 3 minus 33 times 17. So this looks a little ugly, but we can obviously combine these two together. So we get 187 times 3 minus 33 times 17. But you can factor 187 is equal to 17 times 11 times 3. So we realize this is equal to 0. So that's wonderful. That tells us that 3 is the solution to this quadratic, which is all we need to know. So ED, so this value right here is equal to 3. And that is basically our entire problem because we know that ED plus EC is equal to AB. So EC is equal to 104. Great. Any questions about that? You can definitely solve this problem without the power of the point, but it would take you significantly longer because it's going to be a lot of bashing with simply quadrilateral formulas. So the power of the point makes this much easier.
So one comment that we are saying, Rishabh, is does the power of point apply only when the point is inside the circle? Can it apply from outside as well? So I
That's a
think
great question. Yeah, and the answer is it can apply no matter where the point is. So let's draw some diagrams on the next slide. All right, so I'm going to draw 3 separate diagrams here to demonstrate 3 different power of the point situations. So the first one is the one we looked at, which is we have 2 lines, A, B, C, D, and point P in the middle. So we already saw power of the point works with this. The second situation is we have a point A, and then B and C and D. So A, B, C, D. You can see these are the 2 chords right here, but I can extend them out to meet at a point P, which is outside of the circle. And the power of the point works in both of these cases. So what does it look like in the second case? It says PD times PC is equal to PA times PB. So this is true in both of these cases. Well, not really, because I labeled it differently. But the power of the point works regardless if the point is in the circle, is out of the circle. And it's trivially true if the point is on the circle, because the power of the point will be equal to 0, or both sides will be equal to 0. So yes, the power of the point can be used no matter where the intersection between the 2 chords is. And if the 2 chords do not intersect, you can extend them out so that they do intersect.
Thanks, Rishabh. I think in this problem we used the second one, right? So because
yes, sneakily we have used it without making a note. That's a good observation. All right, let's move on to the next question. Great. All right, consider the paths of length 16 that follow the lines from the lower left corner to the upper right corner on an 8 by 8 grid. Find the number of such paths that change direction exactly 4 times, like in the example shown. So let's take a look at the examples they provided. We have this grid right here, which is 8 by 8. And you can see that it bends 4 times. So we start by going right. Oops, we bend up. Now we go back to the right. Now we go up. Now we go to the right. So that's 4 different bends that occur. And in this case, we start by going up, then we go to the right, then we go up, then we go to the right, then we go up. So how do we count how many possibilities there are here? Well, there's one neat observation that we can make, which is this solution and this solution can be made symmetric. So if I take this solution and I flip it across the diagonal, so let me draw the diagonal here. Right? Okay, that's a bad diagonal, but you understand the point. If I flip this square across that diagonal, I get another solution to this problem. But the difference in the solution is that instead of going up first, I go to the right first. So what that tells us is we can consider solutions of this form, count all of them, then multiply by 2, and that will give us all of the solutions. So now that we have that assumption, what do we know? Well, we know that the solution is going to be of this form. So first we're going to go to the right for a bit. Okay, we're going to go to the right for a bit. Then we're going to go up for a bit. Then we're going to go to the right for a bit. Then we're going to go up for a bit. Then we're going to go to the right for a bit. And we don't know how much we're going to go to the right, how much we're going to go up, how much we're going to go to the right, how much we're going to go up, how much we're going to go to the right. But we know that the sum of these 3 is going to be equal to 8, and the sum of these 2 is going to be equal to 8. So we've changed our problem into how many different ways are there for us to put positive integers into each of these squares such that the sum of the first, the third, and the fifth is equal to 8, and the sum of the second and the fourth is also equal to 8. So let's take that to the next slide. So to recap, we know our solution is going to be in this form, our general solution. So how do we figure out how many solutions there are? Well, we know each of these numbers is going to be at least one. They're all positive because otherwise, otherwise I can unify these two rightward segments together, and that would not count as 4 different terms. So each of these are going to be positive, but we don't know what numbers they're going to be. So we can think about it. Let's think about the case of the rights first. So we have 3 different sections where we go right. And we need to distribute 8 right actions between them. So I'm gonna use stars to represent So these stars represent each of the 8 moves that we have to move to the right. And we need to distribute this in 3 different buckets, right? Which we pointed out here. How do we do that? Well, there's a really cute method to figuring out, solutions to this kind of problem, where we have a certain number of indistinguishable objects, and we need to distribute them in buckets. So let me write that down. So we have indistinguishable objects, and we distribute into distinguishable buckets. And the way that we solve these kind of problems is by using a method called stars and bars. So stars and bars is essentially if we have stars which represent our objects and we have buckets that we want to fill, well, all we need to do is right next to the stars, we will add bars equivalent to 1 less than the number of buckets. And you might say, why are we doing this? And here's why. If I think about an arrangement of these objects, so there are 10 objects here, 8 stars and 2 bars. So a random arrangement of these objects might look like this. So when I've arranged all these objects like this, what I've noticed is I naturally have my 3 buckets, right? So my first bucket has 2 objects, my second bucket has 3 objects, and my third bucket has 2 objects. In other words, every arrangement of these 10 objects is correlated with an arrangement of these 8 objects within 3 buckets. So that's a really, really clever insight that allows us to solve this problem. So we can say, all right, how many ways are there to arrange these objects? Well, I'm really just choosing where to place these 2 bars in this pile of 10 objects. So 10, choose 2. But this is not right. And the reason it's not right is because, as I said before, we need to guarantee that each of these buckets has at least 1 right move. So what I need to do is delete 3 of these objects and fill up each bucket with 1 of them. So I need to make sure each bucket has 1 to start, and then we're going to apportion the rest of the objects. So now instead of 10 objects, we have 7 objects, and we're choosing 2 bars. So 7, choose 2. Cool. So this is the number of ways that we can arrange the rightward moves amongst the 3 rightward segments. Now, what about the upward segments? Well, we have the same number of stars. Okay, 1, 2, 3, 4, 5, 6, 7, 8. But because we have 2 buckets, we only use 1 bar. So now we have 9 objects and we're choosing 1. That's not right. Because for each of our 2 buckets, we need to start with 1 star. So I'm going to delete 2 of these. So 7 choose 1 is the number of ways that we can apportion the objects between the 2 upward segments. So our answer is going to be 2 times 7 choose 1 times 7 choose 2, which is equal to 2 times 7 times 21, which is equal to, get my calculator for this. So we have 49 times 6, and that's going to be 294. And that's our final answer. Any questions about that?
Couple of questions. Why specifically 3 buckets?
Great question. So if I go back to the previous slide, let me do that. All right, so in this example we looked at, on the left, we saw that we first moved to the right, then we moved up, then we moved to the right, then we moved up, then we moved to the right. And that gives us 4 different turns. And we realized that in order to get 4 different turns, we either have to go right, up, right, or up, right, up. But we realized that these are really the same kind of movements, just flipped over the diagonal axis. So we're only considering situations like the left, where we go right, up, right. So we have 3 different segments in which we go right. So we need to distribute the 8 rightward moves, right? Because this is an 8x8 grid, amongst these 3 rightward segments. And those are our 3 buckets. Okie dokie, I'll take that to mean we're good to go. So let's keep moving. All right, so problem number 7. Find the largest possible real part of this complex expression where z is a complex number with absolute value of z equal to 4. And with complex numbers, the absolute value of a complex number is its magnitude. So how far away that complex number is from the origin when you plot it on a graph. All right, so this is obviously a complicated expression, but there's an observation that we can make very quickly, which is there's one component of this expression which is multiplied by z, and there's one component of it that's being divided by z. And for those of you who have some level of experience with complex numbers, you will know that we have the following formula, which allows us to compute the absolute value of a complex number. And that formula is the following. Z times the conjugate of Z is equal to the square of the absolute value of Z, or the magnitude of Z. So this is cool, but we actually know what this is equal to. So this is equal to 16. So in other words, we know that the conjugate of Z is equal to 16 divided by Z. So we can plug in the conjugate here in order to make this expression a little bit more manageable. So what do we get? We have 75 plus 117i times Z plus, so 96 divided by 16 is 6. So we have 6 plus, and 144 divided by 16, oh sorry, this is going to be 3, my bad. So this is 3 plus, and yeah, 90, no, sorry, my bad. That is 6. And let me, is there an eraser? No, there's no eraser. Okay, I'll just write this on a new line. Okay, so we have 75 plus 117i times Z plus, so 96 divided by 16 is 6, plus 144 divided by 16, so that's 12 squared divided by 3 squared, or 12 squared divided by 4 squared, which is going to be 3 squared. So that's 9i times the conjugate of Z, and that is our desired complex number. So this is more tenable than what we had before, but it still does not give us an obvious way on how to proceed. But what we can do here is remember the fifth form of any complex number. So for those of you who have seen the trigonometric form of complex numbers, you remember that any complex number with can be represented as follows. So Z is equal to the absolute value of Z times cosine theta plus I sine theta for some choice of theta. And Z prime, given the same choice of theta, is going to be the absolute value of Z times cosine theta minus I sine theta. So let's plug that in. All right, so once we plug that in, we get the following, which is if we set this equal to W, and we have W is equal to 4 times, 4 is the magnitude of this, so we have 75 plus 117i times cosine theta plus I sine theta plus, and actually all in parentheses, plus 6 plus 9i times cosine theta minus I sine theta. All right, so now let's factor this out. So we get 75 cosine theta plus 117i cosine theta plus 75i sine theta minus 117 sine theta. That's the first term here. And then the second term can be 6 cosine theta plus 9i cosine theta minus 6 sine theta, and then plus 9 sine theta. So I can add these all together. And I'll do that right here, in which we'll move to the next slide. So we get 81 cos theta and plus 126 I sine theta plus what is it? Yeah, 69. Sorry, this is cos theta plus. I'll rewrite this on the next slide, but just writing it out. Plus 69 I sine theta, and then minus 108 sine theta. All right, so let's rewrite that on the next slide because it's not legible here. Oops. So we have 81 cosine theta plus 126 I sine theta minus 8 sine theta plus 69 I cos theta. And this is all times 4. Oops. Is equal to W. So this is still a mess, but we then remember that we're only looking for the real component of this. So all the terms with I we can ignore. So we have W is equal to 4 times 81 cos theta, or you can say the real part of W is equal to 4 plus 81 cos theta minus 108 sine theta, which is great. Because now if we go back to the previous slide for a second, we want to see what is the largest possible value here of this expression. How can we find that? Well, we can start with the simple step of factoring. Oops. So when we factor, what do we get? We get the real component of W is equal to, so the common factor here is going to be 27. So 4 times 27 times 3 cosine theta minus 4 sine theta. And the 3 and the 4 here seem relatively suspicious because they suggest to me a 3, 4, 5 right triangle. So let me draw that out. So we have theta here. Yep. This is going to be 5. This is going to be length 4. This is going to be length 3. Then if this is theta, then we know that sine theta is going to be equal to 4/5, and cosine theta is going to be equal to 3/5. Now, why is that important? Well, that's important because it gives us a way of maximizing this function really, really easily. And I'm going to show you that in one moment. So I get my pen working again. Okay, one quick. Right, okay, cool. So if we go back here, I'm going to rename this angle. I have to go back. I'm going to rename this angle I've listed here from, so I've called both these angles theta, but I'm gonna rename this angle to phi. So sine phi is equal to 4/5, cosine phi is equal to 3/5. Actually, let's cross this out. Let's redo this up here so you can see it. So I'm gonna make a triangle like this, have this angle phi. So I'm gonna have this side be 3, this side be 5, and this side be 4. So instead of having sine phi is equal to 4/5, we're gonna have cosine phi is equal to 4/5, and sine phi is going to be equal to 3/5. Now, if I substitute that into this equation, what do I get? I get the real part of W is equal to 4 times 27 times 5 of cosine theta cosine phi minus sine theta sine phi, which some of you might recognize as 4 times 27 times 5 of cosine theta plus phi. And this is something we know how to maximize because the cosine function is at most 1. So this right now is our answer. So this is equal to 540, and that is our answer. Any questions about that? This one was a tricky one to imagine, but the general strategy when it comes to maximizing functions that are maximizing trigonometric functions is recognizing that the sine and cosine function can be at most 1 and at least -1. So if you can write a complex sine or cosine or some kind of trigonometric sum as a single sine or cosine, that allows you to maximize or minimize it much more effectively.
One quick question is, how did you factor out phi?
How did I factor out phi?
Yeah, that's what you explained at the end, but I think that's repeated question, so I'm asking. Yeah.
How did I go from cosine theta cosine phi minus sine theta sine phi to cosine theta plus phi?
No, from 3 cos theta minus 4 sine theta to 5, factoring out phi.
Got it. Factoring at 5. Yes. So I made a little bit of a jump of reasoning, but what you can do here is divide both of these by 5. I'm going to multiply by 5 out here. And then I can replace both these terms by their corresponding sine and cosine replacement. So 3/5 and 4/5.
Yep. Thanks.
All right, so let's switch that. Let's erase these drawings. Let's just do a time check. Okay, we're halfway through. That's good. All right. So the next set of problems I'm going to spend a little bit more time on. I want to make sure that we have an appreciation for the problems. So if there are any questions midway through, feel free to ask them as well. Okay, 8 circles of radius 34 can be placed tangent to BC of triangle ABC so that the circles are sequentially tangent to each other, with the first circle being tangent to AB and the last circle being tangent to AC as shown. Similarly, 2024 circles of radius 1 can be placed tangent to BC in the same manner. The in radius of ABC can be expressed as m over n, where m and n are relatively prime positive integers. Find m plus n. So this looks a little bit daunting. until we realize something which really makes this problem seem like 3 different cases of the same phenomena. And that is the following. If I draw this triangle over here, which I've done somewhat unsuccessfully, and if I draw the in circle, so the in circle is the circle that touches all 3 sides from the inside. So something like this. What you can see is that this example on the left and this example on the right, let me label it here, A, B, and C. And the example that they mention up here of 2024 circles of radius 1 can be placed tangent to BC in the same manner. They're all the same example, except this we've done 1 circle, this we've done 8 circles, and in this example, which I will not draw for obvious reasons, they've done 2024 circles. So that should suggest there's some similarity between these 3 different situations which we can exploit. Now, what would that similarity be? Well, what we really want to do is find some relationship between the length of BC as a function of these circles. Because if we're able to do that, we know that BC is a constant for all 3 of these triangles, and then we can set up an equation. So if I look at these circles, I can draw the centers of the last 2 circles like this, and I can draw a triangle like this. Now, what are the properties of this triangle? Well, I'm going to call this little segment right here, I'm going to call it A. And I'm going to call this little segment B. So how long is BC in terms of A and B? Well, we know that there are 8 circles of radius 34, so there's 6 circles that we have not touched in between these 2 lines. So all of their diameters, we can draw down here. You can see all their diameters contribute, and then there's a radius here and a radius here that gives us this whole segment. So we can write that down as 6 times 2 times 34 plus 34 plus 34, and then plus A plus B is equal to BC. All right, now let's look at this triangle. Okay, I'm going to drop this down here, and now let's look at this triangle on the left here. So this triangle on the left, this one that I've just created, is similar to this triangle right here with the bottom side A. Why is it similar? Well, they share the same angle, and this line that I've drawn is perpendicular to BC in both of these cases. So that tells us that this is a right angle in both of these cases. That's very cool. So what does that tell us? That tells us that by similarity that the ratio of this circle's diameter to this circle's diameter is the same as the ratio of this side to this side. So let's write that down. If I have this ratio, which I'm going to call a question mark for now. So we have A divided by question mark is going to be equal to the new radius, which is R divided by 34. So question mark is going to be equal to 34A. It's going to be equal to if I flip these ratios around and then multiply by A, I get 34A divided by R is equal to question mark. But I can actually do the same thing on this side, on the C side as well. right? If I look at, I'm going to call this question, or I shouldn't call it question mark, but I'm going to give it a label. Let's say y. This should be x, this should be a y, so let's call this x. So if I call that y, then this side, by the exact same logic as we applied for a, is going to be equal to 34b over r is going to be equal to y. And what do we know? We know x plus y is equal to bc. Okay, so that tells us 34 over r times a plus b is going to be equal to bc. That's cool. But what if we applied the same logic to the 2024 circles case? So let's do that. Okay, if we did that, then what equation do we have here? We have 2022 times 2 times 1 plus 1 plus 1 plus, and now in this case, if I look at A and B, then their A's and B's are going to be proportional, and their ratio of proportionality is 34 to 1. So we're going to have A divided by 34 plus B divided by 34. This is also equal to BC. All right, I'm going to stop here for questions. Are there any questions so far? Okay, I'm going to assume the answer to that is no. Now I can set these two equations equal to each other. And let's do that on the next slide. I'm going to bring it out. So we have 6 times 6 times 2 times 34 plus 34 plus 34 plus A plus B is equal to BC, which is also equal to 2022 times 2 times 1 plus 1 plus 1 plus A over 34 plus B over 34. So let's set them equal, right? If we set them equal, we get 33A over 34. Actually, let's try 33 over 34 times A plus B is equal to, so if we put everything else on the other side, what do we get? So we have 2022, so 4044 plus 2, 4046. 4046 minus 6 times 2, which is 12 times 34. So let's do 12, which is 17. So 12 times 34 is 68, yeah, 3468, which is 408. Okay, and then minus 34 minus 34. Okay, so that is equal to 3,000 and 3,600 and 38 minus 68, and that's equal to 3570. It's equal to 33 or 34, A plus B, and we multiply both sides by 34 divided by 33. So 357, let me bust out the calculator for this. I don't want to do this on the fly. So this is equal to 6. So this gives us, when we multiply out, we get so 357 is not divisor 11, so we get, I'm just going to keep it factored. So 3570 times 34 divided by 33, we'll simplify that later, is equal to A plus B. Now, if we go back to the previous slide, so, okay, let's go back to the previous slide. What we remember from our first experiment with the in-circle triangle is that we had A plus B times R is going to be equal to BC, right? And BC, if we plug in this expression into BC, right, which again is 6 times 2 times 34 plus 34 plus 34 plus A plus B is equal to BC. If we plug this in to BC, what we end up getting is we get BC is equal to this is a mess, but this is equal to, so 4048 plus 3570 times 34 over 33. I'm going to leave that unfactored for now. I'll do all the math at the end. So that gives us a value for BC. We divide that by A plus B, which is this expression. And let me just plug that into the calculator. And that gives us 192 divided by 5. And that is R. So our answer is going to be 192 plus 5, which is 197. All right. Any questions on that? Okay. Sounds, yeah, yes.
I think we're good. We can continue. Thanks.
Okay, good. All right.
Maybe we take a short break. 5
All right,
minutes.
yeah, let's take a 5-minute break. Regroup at 8:51.
Okay.
Sounds good. All right, let's begin. Let ABCD be a rhombus whose vertices all lie on the hyperbola as given and are in that order. If its diagonals intersect at the origin, find the largest number less than BD squared for all rhombuses ABCD. So let's draw a diagram for this. So if we have a hyperbola, which it looks something like this.
Which problem are you doing?
Oh, sorry, it's not sharing. My bad. Thank you. Can you see the screen now?
Yeah.
Okay, perfect. So to recap, let ABCD be a rhombus whose vertices all lie on the hyperbola as given and are in that order. If its diagonals intersect at the origin, find the largest number less than BD squared for all rhombuses ABCD. So I'm drawing a hyperbola here, and what we're told is that we pick 4 points and we draw it. Now, what I've drawn is not a rhombus, but it's a quadrilateral. But assuming it's a rhombus, we can label it ABCD, and this is one of the rhombuses that we're looking at. And what we're told is we want to find the largest number such that, say if I label this A, B, C, D, that we want the largest number such that this length right here, BD, which goes through the origin, that number, which we're going to call alpha, so alpha is less than or equal to BD squared. And this is no matter what our choice of rhombus is. So how do we approach this problem? Well, what are the conditions for a quadrilateral being a rhombus? There are two conditions. Okay. Number one is the diagonals bisect each other. So for something to bisect another line means that it cuts it exactly in half. But this is kind of given by the setup of the problem because of the symmetry of hyperbolas. So because they meet at the origin, the length A to the origin is going to be equal to the length C to the origin, and likewise for B and D. So condition one is already given. And condition two is the diagonals are perpendicular. So this is the condition that we need to check satisfies in order to make sure that our quadrilateral is in fact a rhombus. So how can we check this? Well, what we really want to do is see how small can we make BD? And intuitively, the best way to make BD small is to make AC really, really big. And how big can we make it go? So let's move to the next slide and take a look. All right, so I'm going to draw a graph of a hyperbola once again. All right, and I'm going to draw what are called vertical asymptotes. And these are not exactly vertical, but they essentially are asymptotes for both of the hyperbolas. So we'll talk about what the formula for these asymptotes are in a moment. But how big can we make AC? So what I claim is that as we shift AC further and further and further up this hyperbola, it gets closer and closer to being on this asymptotic line. So what we can really do is pretend that A and C are infinitely far apart is on this line. So A is all the way out here, and C is all the way out here on this line. I'm going to call this A, and call this C. Now, what is this line? Well, we're given the hyperbola formula, which is x squared over 20 minus y squared over 24 is equal to 1. And it's a property of hyperbolas that the formula for these vertical lines is given by y is equal to the square root of 24 divided by 20 plus or it's equal to plus this x, and y is equal to square root of 20 over 24x. So these are our two lines which define this hyperbola. So that's great. We can actually simplify this to be square root of 5 over 6 and square root of 6 over 5. So that's great. Now, if we've chosen AC to be on one of these asymptotic lines, then necessarily we need to make sure that B and D are, or that line is going to be perpendicular to the line AC. So if one of these two is line AC, one of these two, then the corresponding lines BD have to be one of the following. So y is equal to minus square root of 24 over 20 x, or y is equal to minus 20 over 24x. And why? Because if I have y equals mx as an equation, the perpendicular line is going to be y is equal to minus 1 over mx. So these are the two possibilities for the line BD. And we're going to consider both of these possibilities as we continue along this problem. Are there any questions about any of this so far? Okay, I'm going to take that to be a no. So let me erase this. So to recap,
Sorry,
we have
one
two.
quick question.
Sure.
How did you find the asymptote?
How did I find asymptote? Good question. So I relied on a knowledge of, or a fact about hyperbolas, that if you have the following form for an asymptote, which is x squared over a squared minus y squared over b squared equals 1, then the two asymptotes are given by y is equal to a over b x, and y is given by b over a x. Those just happen to be the two asymptotes. You can derive it, but it's a rather lengthy derivation. All right. So once we have that, so let me recap what we've discovered here. So the line BD has one of the following two forms. So it is of the form y equals kx, where k is equal to minus square root of 5 over 6 or minus square root of 6 over 5. We don't know which one yet, but that is what we will discover in a moment. So now we want to say, all right, given that we know that B and D are going to be on this line, how small can we make BD, really? So what we really want to see is if we plug in these equations back into the hyperbola formula, how small can we get the distance between B and D? Or in other words, how far or how close can we get B to the origin? Because D is equidistant to the origin as B is. So all we're going to do is plug in our equation y equals kx back into the hyperbola equation. So let's do that and simplify it out. So we have y equals kx, and we're going to plug that into our hyperbola equation. So what do we get? We get kx, so we have x squared over 20 minus kx squared over 24 is equal to 1. So we can multiply both sides by 4 in order to make this a little simpler. So what do we get? We get 6 x squared minus 5k squared x squared is equal to, so we multiplied by the LCM of 20 and 24, which is going to be 3 times 3, 60? No, it's not right. The 24 times 120. Okay, so that's one equation. And then I can plug this in the other way to get an equation for y. So let's solve this one first. So we have x squared is equal to 120 divided by 6 minus 5k squared. And now let's do the same for y in order to solve for it. So we have y over k squared here over 20 minus y squared over 24 is equal to 1. Solving this out, we get 6y squared over k squared minus 5y squared is equal to 120. So that gives us y squared is equal to 120k squared over 6 minus 5k squared. So those are our formulas for x squared and y squared. So what we want to minimize is x squared plus y squared, because if you remember the distance BD, so BD is equal to 2 times the square root of x squared plus y squared. And if you don't understand why that's the case, you can draw a diagram. If I have B, I have D, and this is at point xy. Then the distance from here to the origin is the square root of x squared plus y squared. The distance BD is just double that. So what we want to find the value of is this sum, so the sum of these two terms, square rooted times 2. Now we have two different possible values for k, but there's something that we should observe here, which is as k increases in magnitude, the value of or the value of this sum will decrease or will increase. So if I add these two together with a bigger k, because the sum of these two is an increasing function, this sum will be bigger. So that tells us that if we want to minimize BD, the correct choice of k is going to be this guy. So let's plug that in and see what we get. So we get x squared is equal to 120 over 6 minus 5 times 5 over 6, which is equal to 120. So we can do 20 over 1 minus 25 over 36, which is going to be 20 times 36 divided by 11. If we look at y squared, it's going to be the same thing, except we multiply by 5 over 6. So this is going to be equal to 20 times 5 times 6 over 11. So I add them together, add these two together. So I get 120 plus, or times 5 plus 6 over 11. This is equal to 120. That gives us x squared plus y squared is equal to 120. So our final answer is going to be BD is going to be the square root of 480. I'm bringing this 2 in. So BD squared is going to be 480. So this is the minimal value of BD squared, and that is our answer. Any questions about that?
Don't see any questions on this. Thanks.
Okay, perfect. All right. Let's see, how much time do we have left? We have around an hour. This one will probably take around 40 minutes. Do we want to do that? We can. Okay, I'm going to save this one for later. This is a rather long problem.
Okay.
Let's move on to problem 11, and then we can come back to this. All right, problem 11. Each vertex of a regular octagon is independently colored, either red or blue, with equal probability. The probability that the octagon can then be rotated so that all the blue vertices end up at positions where there were originally red vertices is m over n, where m and n are relatively prime positive integers. What is m plus n? So let's draw a diagram of what they're talking about. So we have an octagon, which actually I should probably not draw in blue. So let's erase that. Make that just a black octagon. I'm going to draw this octagon. Oh, that's a hexagon. Let's try that again. So pretend with me that this is a regular octagon, and we're going to color the points in some fashion. So we're going to put some blue points, say like there, and then we're going to have some red points. There. And we want to see for this random arrangement of blue and red points, whether or not there is some rotation I can make of this octagon so that all of the blue points end up on points that are currently red. So in this case, if I rotate this octagon by 90 degrees, this condition is satisfied because this blue point right here, oops, sorry. This blue point on the top right will go to the left as well as the other blue point on the top. And this blue point on the bottom will go to the right. And all those points are red. So how do we approach this problem? I think the best way to approach this problem is consider each number of blue points as its own separate case. So let's start with a lot of blue points. So if I have an octagon with 5 blue points, so I'm going to recolor some of these nodes to be, let's color them blue. I claim that if 5 or more of the corners of this octagon happen to be blue, then there is no hope of being able to rotate it so that now we have all of the blue points on points that were originally red. And the reason why is because each of these 5 points has to map to a unique red point, but there are just simply not enough red points for the blue points to map onto, right? We have at least 5 blue points and at most 3 red points. So what that tells us is if we have 5 plus blue points, no luck. Great, so we ruled out 5, 6, 7, and 8. That's half the problem done, right? Well, not really, because now comes the more interesting casework. Now I'm going to claim another thing, which is maybe less obvious, which is if you have 3 or less blue points, then you can always rotate to a good rotation. So this is not obvious at all. So let's reset these red points again. I'm going to draw a red point here and a red point here. So what I'm telling you, or what I'm claiming, is that if I have 3 blue points or less, then there's always a way to rotate it into a good rotation. So why is that the case? Well, if I'm able to prove that this is true for 3 blue points, then obviously it's true for less than 3. So let's take the case where there are 3 blue points and 5 red points. So if I have the configuration where all 3 of the blue points are together, then obviously I can rotate it by 180 degrees and I have a good configuration. If I have the case where 2 of them are together and 1 of them is separated by 1, then I can also rotate it by 180 degrees and I'm good to go. If I have the configuration where 2 of them are together, but 1 of them is over here, sorry, is over here, then I can rotate this guy to here, and that is a rotation that works. If this blue point is over here, let me draw it out. Is over here, then the same rotation works as well. And that covers all the cases where 2 of the blue points are together. So now let's take a look at the case where we have all the blue points separated. So I'm going to draw red point, red point. So blue point number 1, blue point number 2. We can rotate this by 1 one side. So this guy, we can move it over here, and this works. Now, what if we have this guy, make it go, this guy's blue. In this case, we can still rotate this by 1, and we are always good. So in other words, if all these blue points are spaced out, then just rotating it by 1 will mean that all the blue points will go to a red point. That's what being spaced out means. So all of that mumble jumble is to say that if I have 3 or less blue points on my octagon, then I can always find a good rotation. So that helps clear out all the cases except the 4 blue point case. Are there any questions with that so far? So let's summarize. 5 plus, no good. 3 plus or 3 minus, always good. Now let's think about 4. So if I have an octagon, let's consider each case by itself. So case number 1 is I'm going to draw all 4 points like this. This works because I can rotate it by 180 degrees. All right, let's draw another octagon. Oh, I'm going to keep 3 of them together, and I'm going to put this guy over here, and this does not work. Why? Well, I clearly need to rotate by at least 2 segments, because if I rotate by 1 segment in this direction, that doesn't work. 2 segments, that doesn't work. 1 segment, that doesn't work. 2 segments, that doesn't work. So I need to rotate by 3. But if I rotate by, let's say, 3 in this direction, then this point goes over here. And if I rotate by 3 in this direction, 1, 2, 3, then this goes over here. So this is not good. All right. Let's draw another octagon. So another case is we have 2 of them like this, and then a space, and then 2 of them like this. And this configuration, I'm going to give you guys a moment to think about. Is there a rotation that works? And the answer is no. Why not? Well, I clearly cannot rotate by 1 in either direction because these 2 are together and these 2 are together. If I rotate by 2 in either direction, that doesn't work either because this guy would go here or this guy would go here. So that doesn't work. If I rotate by 3, that also doesn't work because this guy cannot go here and this guy cannot go here. And I can't rotate by 4 either because then this guy would go here. So that means this configuration does not work. But we still have some more cases to go through. All right. Apologies for the bad drawings, but let's take the next case, which is I put two of these guys together and the other two together, but on the opposite side. Does this work? Well, let's think about it. If I rotate this by 2, we're all good because this guy comes here, this guy comes here, this guy goes here, and this guy goes here. So this is a check mark for me. But we're not done. There's more cases. So let's draw the next case. So the next case is we end up with 2 points like this, and the other 2 points spaced out. So there are a few ways that we can space them out, but the first one is going to be, I'm going to drop one here, and I'm going to drop one here. And this, unfortunately, has no solutions because cannot rotate by 1 for this, cannot rotate by 2 because of this, cannot rotate by 3 because of this. And if I try to rotate by 4, I cannot because of this. This is a bad combination. Okay, now let's go to the next octagon. Okay. Now we're going to consider a case where we have 2 blues again, but now the other 2 blues are spaced out even more. And in this case, we do have a good rotation, and that's the 180-degree rotation. So that works. And there's one final case. We're almost done with casework. And this one final case is where all 4 of them are spaced out. And here we can rotate by 1 and we're good to go. Very cool. All right, so these are all the different cases. And you should check whether or not I've told you the truth or not on this, because you may or not believe whether or not there are more cases or not. But now that we have all these cases, let's compute the probability of any of these cases occurring. Before I do that, are there any questions?
No, no questions.
No questions. Okay, great. So this question, as you can tell, is a little bit of a mess, but most of the questions that are later in the AIME are unfortunately a lot of work in terms of, casework or something of the type. So this is somewhat unavoidable. All right, so I'm gonna clear out the slide and let's do this all very cleanly. All right, so case 1, which we saw, is all 4 together. So I'm just going to call this the all 4 together case. So 4 together, and this is obviously possible. So in this case, there is exactly how many ways in order for this to happen. Let's see, one sec. There's one sec. There is 1, 2, 4. Sorry, one sec, just check the notes. All right, that's right. So in this first case, we have 4 together. So there are 8 different ways that this can happen. And the way you should think about it is if I have 4 points like this, right, I can rotate them all around the circle, and I only need to care about the position of this guy because that determines the position of all 4 of the other points. Cool. So that's the first case. The second case is that the one that we looked at, where we have 3 together and 1 point which is 1 away. So we have 3 together there, one space away, and this is a check mark, so this is good. So this, as we saw, was possible to rotate to. So how many different ways can this happen? Well, it's exactly the same as the 4 together case, because if I have these 3 points and then this 1 point over here, then this 1 point over here determines the position of these 3. So I can pick any of the 8 spots to pick this one straggler point, and the other 3 are completely determined by that. So there are 8 different ways that this can happen. All right. Now what's the next case? The next case is in which, or the next valid case is the one in which we have 2 different pairs of 2 that are up across from each other. So 2 pairs of 2 across from each other. So it looks something like this, and then across the octagon like that. So how many ways can this happen? Well, I would say 8, but in this case, if I pick this point as my starting point and create these 4, versus I pick this point, it's going to look exactly the same. So we have to divide the number of possibilities by 2. So there are exactly 4 different ways that this can happen. Okay. What's the next case? So the next case is where we have 1 pair of 2, and other 2 are 1 away from the pair. So something like this, and then this. So in this case, how many different possibilities are there? Well, we can see that the choice of this point right here completely determines the position of these 4, and that gives us 8 different ways that all these permutations or all these 4 points can be chosen. So that is 8. And that is all of the different valid cases that we have taken a look at. So these are all the different ways that 4 points, 4 blue and 4 red can be arranged, where there exists a rotation that puts all the blue points on the red points. So in total, we have 8 plus 8 plus 4 plus 8. So that is 28 different ways that all of these points can be arranged. And now what we've done here is we've considered all the different ways that we can arrange all the red points or all the blue points, but we can also put all the red points in all these places instead of blue. And we also have valid combinations. So we multiply by 2. So this gives us 56. All right. So we have 56 ways of generating 4 blue points and 4 red points that satisfy the condition that there exists some rotation that puts all the blue points on the red points. I promise this is the hard part done, because the rest of it is quite easy. So now let's do each case by itself, each number of points. So if we have 0 blue points, exactly one way of this happening, and that's good. 1 blue, there's 8 ways of it happening, because it's 8 choose 1. That's good. 2 blue, it's 8 choose 2, which is equal to 28, and that's good. 3 blue, that's 8 choose 3, and that is going to be 8 times 6 divided by 6, so that is going to be 56. That's good. 4 blue, it's going to be 56 as we found. It's great. And we can sum all these combinations together, and that will give us, if we add all it together, 2, 56, 56, so that's 112 plus 28 plus 8 plus 1, so 28, 9. So that's 37 plus 112. It's going to be 149. And there are a total of 256 ways of attributing all the different points on the octagon. Why? Because that each point has 2 potential colors. So there are 2 to the 8 ways of attributing all the different colors to the octagon. So our ratio is going to be 149 divided by 256. The sum of the denominator and numerator is going to be 371. And that's our answer. Let me write that on a new screen. So we have the sum of 0 blue, 1 blue, 2 blue, 3 blue. We have 1, 8, 28, 56, 4 blue, 6, 56, gives us 149, 256, and that the sum of the numerator and denominator, 371, or not 371, sorry, 150, 256, that is 405. And that's our answer. Any questions about that? Sorry, I know the last part was a little bit rushed, but the main complication of this problem is understanding that the casework really occurs in step 4. And once you handle the casework there, then everything else is just combinations. All right, sounds like there aren't any questions, so let's head to the next one. Okay, I'm gonna skip problem 12 because this is also a very long problem, and let me check the time. Okay, it seems like we only have time for one more problem. So I'm gonna pick the shortest one out of the remaining problems left. Problem number 14. All right. Let A, B, C, D be a
Could we go back to that solution again? I think there is maybe calculation was incorrect.
Okay, that is
The previous
possible. Yeah, let me go back. All right, so let me add it all together. So 0 blue is 1, 1 blue is 8, 2 blue is 28, 3 blue is 56, 4 blue. Oh, it's not, I think it's, yeah, sorry, it's 4 blue is 28. Yeah, you're right. It is a miscalculation. So what I incorrectly told everyone was in the 4 cases that you saw. So you saw case 1 with 4 blue together there, then 3 blue together, and 1 away. So this is 8 possibilities. This is 8 possibilities. 2 and 2. This is 4 possibilities, and then 4 separate. This is 8 possibilities. So the sum of this is 28. I multiplied by 2 erroneously because I said that for all the different ways that you can place all the blues, you can also place all the reds. But we've already considered all those cases because these are combinations, not permutations. So when you sum these together, you get 115 out of 256. That gives 371. Is that right?
Yeah, thank you.
Okay, yeah, sorry. Good catch. I should have checked before. Okie dokie. Continue. All right. Okay, let ABCD be a tetrahedron such that AB and CD is equal to square root of 41, AC and BD is equal to square root of 80, and BC and AD is equal to square root of 89. There exists a point I inside the tetrahedron such that the distances from I to each of the faces are all equal. This distance can be written in this form, where m, n, and p are positive integers, m and p are relatively prime, and n is not divisible by the square of any prime. Find m plus n plus p. So let's draw out a tetrahedron. Something like this. All right, so A, B, C, D, and then I. Of course, this is not to scale, but there is something very interesting to note here, which is if I look at every single face of this triangle, they all have one side. So this side is root 41. This side, BC, is root 89. And this side, AC, is root 80. So each of the sides of this tetrahedron has one of each of these sides, root 41, root 89, and root 80. So they're all by SSS or side-side-side similarity or congruence, they're all congruent triangles. So ABC is congruent to triangle ADC is congruent to triangle ABD is congruent to triangle BCD. And that is very interesting because if I draw out a sub-tetrahedron here, so using I as the focal point instead of A, then I can do that for each of these faces. And if I compute the volume of these tetrahedrons, obviously this is true. So the volume of the tetrahedron ABCD is equal to the volume of IABC plus the volume of IBCD plus the volume of IACD plus the volume of ABD. But each of these is going to be equal to R, which R I'm going to say is this distance, which is the distance of I to this plane, which we're told are all equal. So I'm going to call this R. So this is going to be equal to 4 times R times the area of triangle ABC, the area. And this is because all these triangles are equivalent, and then times 1/3. Because the area of a tetrahedron or any kind of cone is going to be 1/3 times height times base. So this tells us that this volume is going to be equal to 4/3 times R times the area of ABC, which is nice, but by the same formula, this is equal to 1/3 times the height, so this whole thing is the height times area of triangle ABC. So this tells us that the height is equal to 4 times this distance R, which we're looking for. So if we find the height, then we just divide by 4 and we get the value that we're looking for, which is very nice. So how do we find the height of this tetrahedron? Let's do that on the next slide. Now, there are many different ways to do this, but I'm going to use vector geometry because I think it's the cleanest approach. So I'm going to draw point A and then the triangle BCD. So the distance H is going to be perpendicular to this plane. So what I can do is, if I make a coordinate system in which I have coordinates for A, B, C, and D, then necessarily I can find this distance H just by coordinate matching. So let's do that. So if we remember the distances that were given, and let me just go back a slide just to make sure that I've done the distances right. So the distances are going to be AB, or so CD is going to be root 41. We have BC is going to be root 89. And let's see, so AB, CD, and then BD is going to be root 80. And that's all the information we need for that. So then now we have AB is equal to root 41, AC is equal to root 80, and AD is equal to root 89. All right, so we can go to the next slide. All right, so with this information, we're gonna assume that the problem has been written in a way where the numbers are nice, and we can observe that if the numbers are going to be nice, then 41 should be the sum of squares. So we just play around with some squares until we find out that 41 is going to be equal to 25 plus 16, 80, 89 is going to be equal to 16 plus 64, and 89 is going to be equal to 64 plus 25. So if we set A to be the point 0, 0, 0, then B can be the point. So we can pick any dimensions here, but AB is going to be root 41 away. So we want to have one coordinate be 5 and one coordinate be 4. So I'm going to do 4, 5, 0. Then we're going to have C, which is C is going to be root 80 away, so 16 plus 64. And then from B, how far away is it? It's going to be root 89 away, so 64 plus 25. So if I choose well, I can choose 0, 5, 8. So let's pick that. Zero, 5, 8, and then D, I can pick to be 4, 0, 8. So the trick here was to observe that these numbers are intentional and they want the numbers to be nice. And that means that they're going to have them be sums of squares so that the coordinates can be integers. So now that we have these numbers, what can we do? Well, in order to find this h right here, what we really want to do is we want to find the shortest distance or the perpendicular distance of the point A to the plane BCD. So how can we do that? So let me over here. Let me erase this slide and rewrite it. Okay, so A is 0, 0, 0. B is 4, 5, 0. C is 0, 5, 8. And D is 4, 0, 8. So with these points, right, and I draw this graph again, I'm trying to find H. What I can do is the following. First, I'm going to find what's called a norm, or first I'm going to use something called the dot product formula. So when I have two vectors, so if I have vectors v1 and v2, I can take their dot product, and that's equal to the magnitude of v1 times the magnitude of v2 times cosine theta, where theta is the angle between the two vectors. So this is v1, this is v2, and this is theta. So this happens to be true in 3 dimensions as well. So that's really nice. But how does that help us in this situation? Well, if I draw out this h, and then if I take a line, let's say this is A, this is B, then if I take a vector that's, let's say, n, which is perpendicular to the plane BCD, so perpendicular to the triangle BCD. Now I take the dot product of AB, the vector, and N, the vector. What I get is AB, the magnitude AB, times the magnitude of N, times cosine of the theta. But let me look at this triangle really quick. What is H in terms of AB and this triangle and this angle up here, theta? Well, AB or H is going to be equal to, the H is equal to AB, the magnitude, times cosine theta. So what I really want, so H therefore is equal to AB dot product with a normal vector divided by the normal vector's magnitude. This is going to be our magical formula, which will get us our solution. Now, the first question you might ask is, how do we get N? Now, N we can get by knowing a tool called the cross product. So we already talked about the dot product. Now there's a notion called the cross product, which is if I'm given two vectors, v1 cross v2, then the resulting vector is a vector v3, which is normal, which means perpendicular to both v1 and v2. So that's how we're going to get our N. So we're going to say N is equal to VC cross CD. Now, how do you compute the cross product of two vectors? The way you compute the cross product of two vectors is using a notion called the determinant. Now, you don't necessarily need to know the determinant. If you want, you can Google the cross product formula right now and remember it. But the way I remember it is using the determinant because I think it's a little bit easier than memorizing the formula. So given a matrix like this, I can have x, y, and z. So these are my coordinates on the top. And then this is bx, so the x coordinate of, or the x coordinate of v1. So actually, let me write it over here. So I have x, y, and z, and then v1x, v1y, v1z, and then v2x, v2y, v2z. And this will allow us to get a formula which tells us what the cross product of these two vectors are. So I'm going to plug in the values as are listed above. So let's plug that in. We have x, y, z. So our first vector v1 is bc. So bc is going to be 4, 0, and -8. And then our second vector is going to be cd, which is going to be -4, 5, and 0. Cool. And when we take this determinant, what do we get? We get 0 in the first coordinate. The second coordinate, we get, no, we don't get 0 in the first coordinate, sorry. We get 40 in the first coordinate. The second coordinate, we get -32. And the third coordinate, we get 20. So I'm going to write this all on a new screen because it's an absolute mess. So we derived that our desired value h is going to be the dot product of AB times the normal vector divided by the magnitude of the normal vector. And our normal vector is 40 minus 32, 20. So we take the dot product of that and AB. Now AB is going to be minus 4, minus 5, 0. So if I dot product these two, I get minus 160 plus 160. Did I do that math right? No, this is not right. This is plus 5. Yeah, this is plus 5, my bad. This is going to be, this one is minus, this one is still minus, this one is plus. So it's plus 160 plus 160 plus 0. This gives us 320. When you take the magnitude of this vector and divide it, let me pull out a calculator and do that. Give me one quick sec. All right. So that gives, so the magnitude of the denominator is going to be the square root of, and I'm going to pull out a factor 4 out so that it's a little bit easier to deal with. So we're going to have 10 squared plus 8 squared plus 5 squared. This is going to be equal to, we have 80 and root 21 over 63, and that is going to be h. And now we divide by 4 to get r. The r is 20 root 21 over 63. And what are we being asked for? Let's go back to the previous slide. We're asked for m plus n plus p, which is 20 plus 21 plus 63, which is 104. All right, any questions about that?
No questions, Rishabh. Yeah, thank you.
Yeah, I think that might have been one of the more intensive problems, but I think the takeaway that you can take from that problem is when it comes to these geometry problems where you don't necessarily have an obvious way of handling them, if the numbers seem particularly artificial, they often are artificial in the sense that they want you to pick coordinates and plot it, and maybe use vectors, maybe use geometry, whatever it might be to solve the problem. So in this case, we ended up using vectors and we used the dot product and cross product in order to solve the problem, but analytic geometry is often your friend, especially when it comes to these later problems. So thank you for having me, everyone. I know it's pretty late, especially on the East Coast. So hopefully this was helpful, and hoping to see you guys in the summer session.
Thank you, Rishabh. This was good, very good. Thank you.
Thank you, Rishabh. Thank you, Savitri and Ram. Thanks everyone for attending. So this, whoever has attended or registered will get a copy of the recording, a link to a copy of the recording tomorrow around the same time. And we will also post this recording on our North South YouTube channel. So please subscribe to our YouTube channel. Thanks everyone again. Good night.